So the next speaker is Yao Yao. She's born in 1985 and finished her master's degree in electronic engineering at the Friedrich Alexander University in Erlangen in 2015. And since 2016, she works as an engineer in Canon Automation. She is the technical secretary of the interest group Layer 1 and 2, in which the requirements and recommendations for the physical layer and the data link layer for the CAN-based technologies are discussed among car makers, tier ones, and semiconductor manufacturers. So a very, very interesting area. And additionally, of course, she accompanies the discussion in the interest group CANopen FD and edits the relevant Canon automation specifications and documents. And her topic, which she's going to present now, is CANopen FD devices identification via new layer setting services, LSS. Okay, Yao, please go ahead.
Okay, thank you, Mr. Schlegel. So then, hello everyone. So as Mr. Philip said, so today I will introduce you another solution how we assign a node ID to a CANopen device, and provide you a short report about the development and the status in the special interest group LSS FD. So at first, I would like also to remind some relevant basic knowledges, and yeah, Mr. Philip has also mentioned something. So as mostly know, and in CANopen networks, there are three types of addresses. So the index and sub-index are the addressing for the objects in the devices and object dictionary. And list addresses contain specific parameters. For example, CA01 defines some objects addresses for COP IDs for diverse services, which contain the CAN identifier, namely CAN ID. CAN IDs identify network-wide CAN data frames and CAN remote frames. And for correctly communicating, as he said, so the CAN IDs for different nodes and for different services should be different. And for CANopen, some predefined CAN IDs contain the node IDs at a lower 7-bit. Each CANopen device shall be assigned with a unique node ID in the range of 1 to 157. So without such an assignment, a CANopen network cannot start operation because devices can't be correctly addressed. So how we assign a node ID, and as Mr. Philip has already mentioned something, there are some conventional methods to do it, some by manual configuration, and for devices which don't have a hardware interface, or for applications requiring a high level of plug-and-play support. So the service LSS Layer Setting Services defined in the CA 305 could be used. So this service offers the possibility to assign the node ID and the bit rate dynamically over the network. But as he said, certainly we need an LSS manager. So before we talk about the service, and when it comes to the node ID assignment by this service, so a basic requirement for participating devices is the availability of the 1018 identity object, so which is defined in the CA 301 specification. And this identity object contains 4 sub-indexes of 32-bit each. They are vendor ID, product code, revision number, and serial number. So together, these make a unique 128-bit value. So this is called LSS address. So of the four indexes, the CANopen window ID is mandatory. So that means every CANopen device need a window ID. And it is a worldwide unique number assigned by CAN Automation. So that then for the next slide, let us see how CANopen devices and CANopen FD devices can be identified by the LSS address. So firstly, how do the LS services for CANopen networks work? So this slide shows the LSS service switch state selective protocol. So as specified in the CA305 document. So you can see the layer setting service distinguishes between an LS manager and the LS server. So please note that the terms LS manager and LS server replace the terms LS master and LS slave in this LS services. So since beginning of this year, and CAA is discussing with this member to avoid avoid the using of critical terms and wordings, so like master and slave. And CAA is committed to use inclusive languages. After half of year discussion on the last CA technical committee meeting, so all experts are agreeing to use the new terms LS manager and LS server instead of master and slave. So because it is decided just before 2 days, so I can't update the whole figures in my slides. So you will still find the old terms in some figures. And if you download or if you need the document CA305, the already released version, you will also find the terms, the old terms, master and slave. So we are now updating all documents according the inclusive languages, but step by step. So, but yeah, it takes some time. And also, if a new version of a document will be made, or if the document is under systematic review, we will also update it right now. So some words, to the topic inclusive languages. So then we go back to the service. So in one CANopen network, there are several LSS servers operated. So for this situation, if LSS manager has known the LS addresses, the address of one specific server, the LS manager can address this server by means of this switch state selective service, as shown here in the protocol. And the vendor IDs, product code, revision number, and serial number are sent in 4 data frames in sequence. So the LS server with the same LS address will be switched into LS configuration state so that the LS manager is able to modify the local layer settings. So for example, the node ID. So for the situation, if the LS address is unknown, so there are 2 mechanisms specified in CA305. So solution 1 uses the identify remote slave service. So this solution briefly is that the LS manager will propose a vendor ID and a product code and the range for the revision number and the serial number. Then the LS manager narrows the proposed LS address range. After several scan cycles, the LS manager can have a single LS address. So this solution uses long and limited scan cycles. So we don't use this solution mostly now in the praxis. So I will not introduce it in detail. So to mention it, I would like only to show the development steps. So solution 2 is the Fastscan service. So this service use only one message. The ID number will contain one of the 4 parts of the LS address. So the vendor ID or the other 3 parts of the LS address. So they will be bitwise scanned. If there is at least one response from LS servers received, so the bit is set to 0. Otherwise, the bit is set to 1. And for acknowledgement, a 33rd response is required. That means for the complete NO LS address, we need 33 times times 4 equals 132 data frames. So that means also, yeah, the Fastscan is not really so fast. So since CIA has published the 1301 document, the CANopen FD application layer and communication profile in 2017. So the CIA technical group SIG LSFD is discussing how CANopen Layer Setting Services should be adapted to CANopen FD. So this special interest group is also initiated by more than 3 members. So I think there is still interest to use some companies or some implementers have the interest to use this service. So then the feature of CANopen FD to be used is the extended payload of the 16.4 byte. So the new service adapted to and used for identifying CANopen FD device. So it's the new service names as an LSS switch state selective FD. So, and in order to understand the new service, we should firstly understand the definition of NEBOs. So you can see here the abbreviation NIB. This stands for NEBO. So for the purpose of identification, the LSS address is divided into an array of 4-bit values. There are 32 NEBOs and they are numbered from 0 to 31. And start from the most significant bit of the vendor ID and end at the least significant bit of the serial number. So the parameter NEBO number indicates the NEBO to be checked and is this parameter. So indicates the NEBO to be checked and is sent in the request by the LS manager. And a special case of NEBO number equals 32 is used to acknowledge the full 128-bit LS address. And another important parameter in the LS manager request is portion. So portion stands for portion LS address and is a 128-bit value. So which indicates the already determined LSS address. So this is benefited from the expanded payload up to 64 byte from the CANopen FD. So as shown here in the diagram, and with the 128-bit parameter portion. So the LS manager request has in total 20 bytes. The service goes like this. The LS manager asks all LS servers in the network. So here are the first n neighbors of the LS address. Does any device have a match? If yes, the LS server will answer with one of the 16 response messages. The response messages don't have any data, but this message contains the information about the value of the next NEBO. So as specified in the equation of the CAN ID of the response message. So because neighbors are all 4-bit values, therefore the value range of one neighbor is from 0 to F in hexadecimal. Using this response message, the LSS manager can get the information and which value this to be checked neighbor has. The value of the full LS address is then checked neighbor by neighbor. So for a better understanding, let us see an example on the slide. And in the example, the LSS manager sends a request and would like to check the value of neighbor 3. The portion LS address as shown and contains the value from neighbor 0 to neighbor 2, and they are already determined. In the LS manager request message, the value of the parameter neighbor number equals 3, and the higher bytes of the, so that the higher bytes of the portion LS address equals 6006 in hexadecimal. So then all LSS servers receive this LS manager request with this portion address and make the comparison with its own address. So if the value of the neighbor 0 to neighbor 2 of the server matches the value of the manager, so then this LS server will transmit and identify a response using the CAN ID containing the value of its neighbor 3. So to see this sequence diagram of this example, and you can see in the LS manager request message, the value of the parameter neighbor number equals 3. And the higher bytes of the portion equals 006. Then the LSS manager use the CAN data frame format, base frame format, and use a fixed CAN ID 7E5. So the LSS servers get the requests, and after comparison, if the values matches with each other, then this LS server sends a response with CAN ID containing the value of the neighbor 3. So the CAN ID of the response is calculated as the rules here, and this CAN ID equals 70 plus the value of the neighbor 3, so plus D is 7DD. So the LS master gets this response and processes this response and packs this value of the neighbor into the next request. So as the diagram shown, the LSS manager sends the next request with the neighbor number 4 and the portion address with the higher bytes 006D. So to check the value of the next neighbor, the neighbor 4. So that is how the service works. Another important parameter of this service is team, so which I have not introduced. So this parameter team stands for the LSS manager timeout. So within this time, the servers shall generate one LS response. The maximum alone timeout is specified in the range of 1 millisecond to 100 milliseconds. First test implementations have shown that if both LS server and manager are capable of real-time behavior below 10 milliseconds, that means the server replies to the manager requests in less than 10 milliseconds. So the detection of an unconfigured device and assigning it a node ID can be completed within less than 350 milliseconds. So this is a significant improvement in comparison to the previous Fastscan mechanism that took about 1.4 seconds to complete using a 10 millisecond timeout. So after introducing the new service, I listed here the use cases that we could have when the LSS manager requests the switch stay selective FD service. So for different use cases, the values of the parameters portion, LS address, and NEBO numbers are shown in the list. For the use case, if the LS address is completely unknown, completely known, so we should set the portion LS address, the or known LS address. That means the value of from neighbor 0 to neighbor 31. And the neighbor number should be set 32. This is the special case, the special number to conform the received, the checked a full 128 bit of the LS address. So the second case is if LS address is not entirely known. So certainly we set the portion address to the partly known LS address. And the neighbor number should be the first NO neighbor number. So for the use case, if the LS address is completely unknown, so that means we don't have any value of a neighbor. So this is still not used when we set them or 0. And we should ask for the value of the neighbor 0, then set the neighbor number to 0. So you can see for the worst case, if the LS address is completely unknown, so we will need 32 pairs of requests and response for the 22 neighbors, and plus one pair at the end to confirm that the full LS address is checked. So in total, 33 pairs of requests and responses. So it is much effective than the services as specified in CA 305. And at the end, we can say the idea the ideas from the experts in the working group for the new service is to gather the advantages of the principles of the service switch state selective and Fastscan, and to get the advantage of these principles and to make it better and effective. Okay, to sum up my speech, and in general, the new service makes the operation sequence of identifying LSS server simpler and more flexible. And the LS switch state selective FD service will be specified in the CA 1305 document. And so this document is already technically stable for several months. Because of the current situation, the release is somehow delayed. So we will accelerate the further works and steps and to release this document expected in August or September this year. So to that, we will update the document according to the decision of the new terms of LS manager and server, and make editorial improvement and then release this document. And at the end, one important thing is the CA 1305 document. It's not backward compatible to the CA 305 document, while CANFD is not backward compatible to CAN. Okay, so this is all from my side, and thank you for the listening.